So today was listed as a bit of a review week that was supposed to be decided by group consensus. Part of the issue there is that I didn't necessarily post a poll to let people know that they could choose what to cover for the class today. And so I figured a nice fallback would at least be to continue on with the exam 2 that we were running through over the past week. If there's anything you'd rather me have a look at, happy to do so. But I feel like this also gives you a nice broader overview of all the kinds of questions that are going to come up. And at least at this particular spot we left off, it is pretty topical, given that most people are either doing probability currently or are coming out of having done probability. So let me know if there's anything you want me to go through, but otherwise I've put us not exactly where we left off, because there's a bit of like background information you need if I were to do exactly where we left off. Here at H would be a good place to start because you don't need to know anything previous to achieve that. So what I'll do is I'll drop the exam 2 in as well as the solutions, so you don't have to look at my screen share for anything in particular unless I specifically mention it. Let's see, is that going to download? It's getting there. There we go. Cool. Okay. Both grade A and grade B balls. That is a bit of background information, but not particularly necessary. All you really need to know is that the serving speed of the grade A ball is continuous, random variable, as it says here, and it's given by this piecewise function. That's the only thing that actually gets asked about in the context of these questions here. So have a think. I think I just had another join, so I might have to drop those in the chat again, because I'm pretty sure the chat doesn't persist. Drop that in one more time. And PO, we're moving on to H now, essentially, unless you want to do anything else. It's supposed to be a review week. I didn't really mention that ahead of time, though. Find the probability of the serving speed being greater than 50 meters per second. Reminder, this is tech active, by the way, exam 2. Serving speed being greater than 50 meters per second. Probability of that thing occurring. That can really narrow your focus, so maybe have a look at your notes on continuous probability if you have them, or otherwise have a think about what that might mean. Anyone's fully stuck, feel free to let me know. Otherwise, maybe a thumbs up if you're still working on it and making at least somewhat progress. Maybe fully stuck. Okay. So when it comes to continuous probability, we're pretty much exclusively using integrals. When it comes to finding a probability of a certain thing occurring, it's going to be the integral over the domain of that thing occurring. So let's say we're going to find the probability of x being greater than 1. We would have 1 as a lower bound, infinity as an upper bound, and then whatever f of x is in the integral, and then that will equal your probability, whatever target probability you're looking for. That's if you're calculating probabilities, which is what we're doing here. So with that in mind, there's only a few things that need to change there. What needs to change? Lower and upper bound, correct. Yeah. What do we have to do as our lower and upper? 3 pi power 2 plus 30. Yeah, that's going to be one of the terms. That's correct. Yeah. What's the other one going to be? 30. Well, that's the full domain. So from 30 all the way to 3 pi squared plus 30, that's the full domain. We're looking for a very specific probability. We're looking to exceed 50 meters per second. So
Where the function equals to 50.
say again, sorry?
Is the lower bound going to be like wherever the function is equal to 50?
The lower bound is going to be specifically 50, not where the function equals 50. And the reason why is because when it comes to continuous probability, the x-axis is the outcome, right? Like these are speeds. So your v for velocity, speeds, continuous variable v for the serving speed. So when you want serving speed to be greater than 50, it's a bit different than how you normally have it in functions. Because usually, like, some function is y-axis is quantity and x-axis is usually time or something like that. With continuous, a little bit different. The quantity of interest is on the x-axis, but the probability of that thing occurring is given by the integral of the function. So when we go about it, we're going to have that 50 as the lower bound since we want to exceed 50 meters per second. Then we're going to have our 3 pi squared plus 30 is the upper, and then the entire function in here as the, as the function. So 1 over 6 pi sine square root x minus 30 over 3, and yeah, just dx. And that's going to give a nasty answer. Good thing it says give to 4 decimal places. And so that's a lot more easier to manage there. Yeah, so in summary there, whenever you're trying to do a continuous probability, and you'll know it's continuous because it'll either tell you it's continuous or it's going to use a function to describe that thing. When you know it's continuous and you're trying to find a probability, it's going to be integral with upper and lower bound given by the parameters in the question. We'll see a bit later, there's other stuff that you can calculate as well, like the mean, for instance, in part I. Pretty much all of continuous is going to be using integrals. In fact, if you have a look at your formula sheet, it'll at least help you with... Oh no. Wait, yes it does. There we go. Continuous. It helps you with the calculation of continuous probability, mean, variance, and technically also standard deviation because, well, it's always just square root. So you have all these things here, and you should have a copy of the of the exam as well. So see if you can use specifically this one for the next part, calculating the mean. Find the exact mean of the serving speed. Yeah, we're just going to times it by x. That's one big thing that needs to change. So instead of doing the function just itself, we're going to slap an x at the front or at the back. Same thing, you're just going to multiply by x. But there's one final thing that has to change if you're looking at my CAS. There's a little bit of a difference in there. I'll leave it at that for now. If we don't come up with anything, I'll give a hint. The hint is that part H and part I are different. So the information in here has nothing to do with the information in here. Part I uses this up the top, not the H section. That should help you identify which part of this integral needs to change still. The 50 goes to a 30, correct, yeah. So when you're doing mean, you ignore, well, I guess the real answer is when you're doing mean, you use the maximal domain of the function. And so all we're going to do is go back to the end, change that 50 to a 30, and then we're able to do exactly what you said there, which is just stick an X at the front. Put it at the front, put it at the back. As long as it's in the brackets in there, and it's all as a multiplication of the entire function, it doesn't really matter where that goes. It does say find the exact mean, and so you would give exactly this as your answer. 3 bracket pi squared plus 4, or if you really wanted to, you could expand that out as well. That's fine. Fully factorized or fully expanded is pretty much the standard you have to meet when presenting your answer here. If there's any questions about that, feel free to let me know. Otherwise, we can get into probably the most complicated of the probability questions here, because it's not really a probability question. It is a transformations question. So we'll see how we go. I'm happy to also field ideas as well. You don't necessarily to come off mute with the answer off rip. Just some ideas that could at least get you a bit closer. We've now got a new ball. Oh, no, wait, that's just the disconnect. We've got a new ball that's being described. Again, it's still going to be continuous. Different probability density function. The density function of the new one is a transform version of the old one. So you've got this A, you've got this B as the key things to solve for. And because it's G of W, it essentially means that the W in this is the same as the V in this. Right? It's just like, it's kind of like an X, right? Just a thing that the function is describing. And so this isn't really another thing that needs to be solved necessarily. It's the same as if it was like a V in there. So really only things that are slightly different here are going to be the A and the B. So that's one thing. G of x is the same as f of x with respect to, well, after having applied the transformations of A and B. We're also told a known quantity of our grade B ball, which is the mean is specifically going to be 2 pi squared plus 8. So we're told off rip what the mean has to be. That's the key information that we have. The last hint that I'll give before shutting up for a bit is going to be that you have 2 unknowns. You've got 2 unknowns, 2 equations is usually what's required there. Any ideas on how I could create a single equation? There's definitely one piece of key information in here that could help us create an equation. In fact, we did it in part I. You know how to solve part I, you can at least create one equation in J. Or at least you can get very close to an equation in J. Okay. Well, we're told the mean, so if we have a method of calculating mean, we should just integral of function times x, or I guess in this case times w, then that's our first equation. W times g of w, or the integral of that, is equal to 2 pi squared plus 8. That would be the first logical equation you could create out of this. Let me just take a sneak peek at the answer so I don't give too much away at the beginning. Yeah, okay. Now that definitely gives you an equation that you can use, but there's one little thing that's present in here that makes life a bit harder. So for instance, if I start drawing out what would naturally be the integral here, you would have the integral from, we'll leave it blank, the integral, because that's what's going to change a bit, and just w times g of w has got to be, oh, come on, refocus, there we go, equals 2 pi squared plus 8. 2 pi squared plus 8. Now, we can't just put 30 and 3 pi, whoops, 3 pi squared plus 30 on these, because there's a transformation applied to w. All right, there's a transformation applied to the x-axis. Specifically, you have where v used to be is now w over b. Where v used to be is now w over b. And so that actually affects these terminals. And the way you can figure that out is by comparing to the initial inequality. If what you used to have was 30 less than v less than 3 plus, yeah, oops, let's fix that up to be in the right order. 3 pi squared plus 30, then now instead of putting a v there, you now have w over b in that spot, because v is the same as w over b. And so to now rewrite this inequality as something that actually makes sense, you would multiply both sides of your equation by b. But because there's two inequalities, you're just going to stick a b on both sides of that. 3 pi squared plus 30b. And so that's the only other thing that would be a bit of a barrier that will get a lot of people. The fact that you also have to stick b on both of these functions, on both of these terminals, rather. That's also implicit in creating your equation for the mean. Now, I'll show you what that actually ends up looking like with something pre-written. Let's see here. Go too far. Yeah. Oh, might have given it away. Anyway, focus here instead. So instead of saying, instead of being able to say g of w, we now have to replace that in terms of the original function, because we're told that g of w is a times f of w over b, so we're just going to put the original function at that spot. So there's your 1 over sine and all that sort of stuff. You're now going to have w, w over b, w, and even the a as well. So you have the A multiplying the entire thing, like you would expect, and then every V is replaced with a W over B. So that's that one. Except for this, that doesn't really count, because this gets subbed into the function, whereas this is because we're doing me. There's a fair bit involved there. Does that need to be explained in any more detail? A lot. Definitely a low percentage solve question. In either case, that gives you the first equation. You've got this key piece of information that's able to be slided straight into a mean equation. The only nuances there was the simplification around the transformations. The other key equation comes from, now I'm going to try and think about how to word this so it doesn't immediately give it away. It's another equation kind of like this in the sense that it exists in the formula sheet, and it's something true of all continuous functions. So you always have this equation no matter what when you're dealing with continuous functions. You can always slide it in somewhere. So if you're not immediately getting it, think about what's true of all continuous functions, or what's like a prerequisite for a function to be a continuous probability distribution. Let's see if it feels some. What are some fun facts about continuous functions? What has to be true in any type of continuous function? In the context of probability being continuous anyway. What are some of the rules? Or even just some basic probability rules. And then we'll retrofit them back to being in continuous probability. Oh no, nothing. That's fine. So the other one's just going to come from the fact that all probability has to add up to 1. That's true of all probability, also true of continuous. And so the way to represent that in continuous is to say the integral over the full domain has to be adding up to give 1. So you're still going to have those A and W over B type stuff, but what you're not going to have is the mean portion of it. That multiplied by W is now disappeared, and you're replacing that with an equals 1, because the entire probability has to equal 1. Reminder, of course, that probability for continuous is given by doing your integral domain, the integral of that full domain, and that has to therefore equal 1 because you're doing the entire domain. So you got equation 1, you got equation 2, CAS solve with the simultaneous equation solver, and you're going to get that. Literally as written, exactly as you see here, even if it looks like shit. If you plug that into your continuous probability, in your simultaneous equation solver, you'll get these values. I'm curious, what was the pass rate on this one? Because it was definitely low, and I think the thing that would have got me when I did it the first time would have been this domain thing that had to come out. Everything else, you'll eventually get the intuition that you'll have to, equal things to 1 or create your mean equation. This domain bit was a bit of a killer though. Let's see. I'll bring up the exam report and see what the pass rate was. Question 4J. 5% for 1 mark, 6% for 2 marks. So if you were totally lost, then just know that 89% of other people were also totally lost. But the good news is, if you now understand it, or at least roughly understand it, and can then start working on it, you'll now be not part of the 89%. Okay. that'll mark the end of the probability section of this one. So if there's anything in there you still want me to clarify, please let me know. Otherwise, there's another transformation thing, but it's not nearly as bad. Part of the skill here again is going to be to note that we're going from F to G, and G of course is a transformed version of F. You can see it's got some factors in there that would cause transformations. Really the goal is just going to be in making sure you order them in the right way. You're forced to start with the dilation factor of a half, so that's clearly going to hit that one for you. The rest is going to be figuring out which order you do these in. The other hint's going to be that there's technically two valid answers here. Yeah, there's two valid ways of doing it. Part A or Part B? Let me double check. What was it? Yeah, Part A. Up to Part A. Even if you don't give the order immediately, what transformations do you see that's being applied to F here? Would it be translating 2 units left and a reflection in the x-axis? Let's see. Translate 2 left and then reflect in the x-axis. 2 left, then reflect in the... not a reflect in the x there. Not quite. Because reflecting in the x would mean... Yeah, correct. Reflecting in the y. Reflecting the x would mean a vertical from top to bottom. When it's directly attached to the x variable, you're flipping left to right. And so yeah, translate 2 left and then reflect in the x is appropriate there. That's one way of doing it. You just read it left to right, nice and easy. Typically speaking, most people end up doing a DRT type method where you do the reflect first and then the translate. The only challenge with that, of course, is that you have to do a factorize. You have to take that negative out the front. So if you do it that way, this is what you did, which was just eyeball it, which is really good. It's a really good skill to be able to eyeball it. If you do your whole x dash y dash type stuff, you can get it to look like this. That's a lot to do. More so was observing this, taking that negative out the front, and then you can do your yeah. Then you can do it that way. Either way, same thing. Sweet. All right. If there's anything to clarify, let me know. Otherwise, this time part B. two functions g1 and g2. So both of them are the same thing as g, different domains. g1 is the strictly increasing portion of it, and g2 is the strictly decreasing portion of it. We're specifically caring about the domain and range of the inverse of g1. So g1 is strictly increasing. The inverse of g1 is a bit different. Because there's two parts to this. You've got two marks. I'd first be worried about getting an understanding of what g1 and g2 are, and then what it would look like to find the inverse of them. We've done strictly increasing and decreasing not long ago in this exact exam, actually. Um,
Chris, could you would we have to set up some sort of example to help us visualize, or is there a proper way to do this?
you won't even need an example, you've got the functions.
Oh wait,
So,
hold on. Oh, it's from this function. My
yeah,
bad.
yeah,
Yeah, okay.
all good. Remember, you've even got the CAS as well, so getting a plot of what g of x actually looks like wouldn't be too hard, because you would just plot, or you just define f and then define g as exactly that. Then if you get a plot going, you can very quickly see where the strictly increasing and decreasing parts are. You might not get the exact value from the graph, but you can at least see what's going on a bit better.
Chris, I plotted G, but I didn't really find a section where it was strictly increasing.
Okay. Did your g look like this?
Let me see. No,
Okay.
mine looked like a negative cubic.
Interesting. Okay. So, did you define it in two separate parts like this, or did you just try to go straight for substitution?
Yeah, I'll try to go straight in.
Yeah, okay. Um, cool. Because if you do straight substitution, what do you have to do? You do like 0.5 bracket e to the 2 minus x plus e to the, what is it? E to the negative bracket 2 minus x. And with any luck, if I print g of x again. Yeah, okay. Maybe just double check that on your CAS if you put that in right.
Oh no, I got it wrong, my bad.
Yeah, all good. But okay, so either way, you're going to get something quadratic looking. From there, fairly obvious where the increasing and decreasing parts are as far as their domains. Um, how do you, if you wanted to get an exact value rather than using the graphing tools to just see it, how do you know where you've got strictly increasing or strictly decreasing?
You want to find the turning point?
Yeah, find turning point. Really good. That's why having a graph is kind of helpful there, because you can, instead of saying like double derivative equals zero for, also double derivative equals whatever for strictly increasing or decreasing, um, you can then just go for the, did I say double derivative? No, it should be single derivative being positive or negative. Anyway, um, point being, you can now just sort of shortcut that to just doing derivative equals zero. Yeah. So derivative function equals zero. Probably should have put a solver around that, huh? And that one ends up being a nice number anyway. So even if you did use the graphing tool to find it, you would still get x equals 2. So that's fair enough. That gets you x equals 2 for turning point, and then obviously strictly increase is going to be everything right of that, and then strictly decreasing is going to be everything left of that. That gives us our G1 and G2 split. We really only care about the G1 split, or specifically the domain and range of the inverse of G1. So we only care about, if I were to now fix up this graph a bit, we're only going to be looking at the left-hand portion of it. So all x less than equal to 2. More specifically, the inverse of this. So what's the main rule around finding domain and range for inverses, just across the board?
We switch the domain with the range.
Yeah, correct. You find the domain and range of the original, and then you swap them to get the domain and range of the inverse. Precisely. All right. Let me know how that goes. Oh, hang on. No, made a mistake. It's supposed to point right instead of left. I misread the question. It was domain and range of inverse of G1, and G1 is the increasing portion. Whoops, my bad. Well, there's two things you got to give. One's domain, one's range. 1 to infinity is one of those values. Yep, that's good. Which one is 1 to infinity? Domain of inverse or range of inverse?
Would it be domain?
Hmm. Yeah, that's the one. Because it was range of original, so obviously then flip that to be domain. Yep. Last up, need the range of the inverse.
Is the range 2 to infinity?
2 to infinity. Yeah, correct. With my updated, making sure I was pointing in the right direction there, the increasing portion of it. Now, bit of a fun fact on this one, they didn't actually specify that you had to maximize these. So technically speaking, you could have actually done a subset of anything between the 2 to infinity and then went from there. It's obviously a lot easier to maximize it because you can just see it. So yeah, whether you put square or circle brackets on this, you technically could have done either and anything in between. If you wanted to maximize it though, square brackets is where it's at for the for those endpoints. But otherwise, yeah. Did it go on you? Yeah. Okay, that's where it went. I just forgot to highlight it green. Cool. Alright, so that's that part then. You got G1, G2 are the strictly increasing and decreasing portions of those, so it's good to then split off into the part that you actually care about, and then from there start working on the inverse portion of that. Here's what that all looks like. So you've got the parabola-like shape of it. So that would be a nice way to self-correct yourself in the actual exam, by the way. So let's say you're doing that question in the real thing, you're drawing a blank, or you've drawn a graph that looks a bit weird. If you then looked over to the second page, you'd actually see what g of x is supposed to look like. So that's a way that you can self-correct. But yeah, here's the portion. So you got g of x as the bold one, you've got the inverse of g1 as the solid line, and then you've got the inverse of g2 as the dotted line. Yeah. Intersection points are labeled P and Q. So those are the intersection between the inverse and the original. First up is finding those coordinates. So where does the inverse intersect the original? Yeah, I'll leave it at that for now. See how much we remember from our functions and relation stuff.
Can we make the original equal to x? And then
Yes, that's the better way of doing it. So any two functions will be equal to each. Oh, sorry. The intersection point between any two functions can be found by equating the two functions together. Now, you've gone a step beyond and said, hey, look, if I grab the inverse of g2 and equate that to g, that's a pain in the ass because not only do I have to now find the inverse of g2, but I know it's going to be a lot of effort to actually make that solve. And so realizing that inverses always intersect along the line y equals x, so you can see that q and p both exist on that dotted line y equals x, you can skip having to ever try and solve the inverse and just go straight to saying g equals x, right? G of x equals y equals x, because that also is a common thing across both p and q. Yeah, really good. So if you do that, you're going to get your two x values. Now, reminder, that's just x values. You need the full coordinate. I'm curious if you see a shortcut for getting this coordinate as well. You're going to have your two x values there. Hoping that AI, yeah, there it goes, disappears.
I think your y value might be the same as your x coordinate.
Sure will be. Can you explain why?
Y is equal to x.
Y is equal to x, yeah. So rather than sub it into the complicated function, you sub it into the easy function. And the easy function, of course, is that, well, y just equals x. And so sure enough, whichever one you give it into, you're going to get the same value. Not that it really matters too much in CAS, because you already have this defined. But yeah, sweet. That's a good one. Okay, you're going to be using a similar sort of thing for double I here. Find the area of the region bound by G, inverse of G1, inverse of G2. So a reminder that these things that are mentioned essentially form the perimeter of your shape. So you've got inverse of G1, inverse of G2, which is that, and then G. So what that effectively means is, where do all those lines meet? Well, it's this bit in the middle here, this little buffer type shape. Finding the area bound by that. This is obviously going to bring us back to calculus type stuff. Area bound by graphs.
Chris, I don't have an equation for you right now, but
Mhm.
is it gonna be the like okay, so the derivative, sorry, the integral of G1 take like inverse of G1 take inverse of G2 over the domain of 1.27 to 4.09.
If you do it all the way to 4.09, you're doing it all the way to Q. And that would mean you'd find area where G1 is your top, G2 is your bottom. So you'd be finding also this vertical line here. You'd be shading all. Can you see my cursor?
Oh yeah,
Yeah.
shoot.
So you'd be shading all of this underneath the solid black line as well. You'd have the inverse of G2 as your floor for that whole thing. So it's a good idea. You do want to just do top take bottom there. You just got to keep in mind what bottom actually means. Because G2 will be bottom for a certain portion, but not for the entire portion. Just got to remember your shape is this little oval type thing here, not just G2 to G1. So just sort of like trace the underside of the shape, trace the overside of it, and then realize which one's which. You'll notice there's a handoff. I think I'll just leave this one here instead so you can see the shaded region we're looking for. If you're struggling to figure out what's going to be bottom, what's going to be top, think about it in terms of complete vertical line strips. Like if you imagine this vertical strip here, yeah, you've got G1 on top of G2, right? If you cross vertically straight down, the first line you touch is going to be the top of G1, and the last line you touch that's still in the green is going to be the line of G2 inverse. But if you draw it down here, the first thing you touch is still going to be G1 for top, but the last thing you touch that's still in the green is actually going to be the G of X, the solid black line. So when you get to this stage, G of X is your bottom. So if you were to try and split it into a top take bottom scenario, you're basically doing it in two parts. One, which is from here, where your top is inverse G1 and your bottom is inverse G2. And then from here on, where your top is inverse G1 and your bottom is G for the remainder of the thing. Perfectly valid way of doing it. The challenge you run into is kind of like what we had before, which is finding the inverse of G1 and inverse of G2 is a pain in the ass. I'm not even sure if you can because it's you may or may not be able to algebraically solve. I'm sure you could, but it is tough. The CAS may or may not do that all that well. So there is a shortcut instead of taking that approach. Just to sort of refresh your memory, you can use symmetries a lot of the time for area stuff. What kind of symmetries might make life a lot easier? Think about the line y equals x is definitely going to help us a lot when it comes to finding the area of the entire thing. Um, if we only find a portion of an area and then use symmetry to solve the rest, that will be the fastest way of going about it and the easiest.
Chris, I don't know if they're even, but say if we did like integral with y is equal to x, take g of x
Yep,
over 1.27 of 4.09,
yep,
and then we multiplied that result by 2 to
yep.
get the whole thing.
That'll do it. Yeah. And the reason why you can be certain it's symmetrical is because this is an inverse pair, right? G of x is its own function, and then g1 and g2 make up the inverse of what g would be if it was a function. Obviously, it's a relation because it's a sideways parabola. But because you know that y equals x runs through the dead center of this, it's an inverse pair, then yeah, you can be pretty certain that the top and bottom are perfect halves. And so that's what you end up doing. So you still do your top take bottom, but because you've only got one top and it's an easy top, y equals x, you're just doing this portion here. You got an easy bottom, you've already solved it. Yeah, you're just doing integral top take bottom and then slapping a multiplier of 2 on there. Nice. Um, I'm not entirely sure it's even solvable if you do try to go through the inverses this way. I'm pretty sure. Let's just try it. Let's see what happens. So if yeah, okay. The issue you're going to run into is when you try to do your swapping of x and y, and try to CAS solve it. I don't think the CAS is good at giving a relation as an answer. Let's see. So if you were to do it, you'd do something like x is equal to g of y, and then solve for y. Pretty sure it's going to give me nothing. Yeah, that's. I mean, it's probably technically correct what they got written there, but you know, the y is of course not on its own.
Chris, just a question. Like when we get our own number, like 5.56, do you think for like a exam it would be valuable to write it as unit squared? Or
Um, yeah, I mean, look, it can't hurt to put unit squared in there. If I have a look at the prescribed answer in the methods report, they don't ever actually put unit squared on anything. Um, yeah, I've never actually seen unit squared in a in one of the VCAA exam reports, so I'd say it probably doesn't matter. Um, you might, yeah, area. VCAA don't seem to care. I'll say that much, but I won't say it'll hurt. It'll it'll either be nothing or a benefit. Unit when you put in a unit, It's more so if they've like specifically put units in there. That's when it matters a lot. In the VCAA exam reports, I don't seem to care. Okay. Another transformed version of f. So minor, this is still the same f of x that we had up the top, which I'll reprint on my CAS. Oh wow, it gives me cosh. That's fine. Okay. Maybe I'll reprint it this way. There we go. Yeah, there's a little fun fact for anyone who is interested in spec stuff. That's definition of 2 cosh. Anyway, so that's the original f that we're transforming. We've now got k minus x and 1 over k. So last time it was 2 and 1 over 2. Now let's replace at the k's. Turning point of h always lies on this function. Find the value of n. That looks fun. This will probably round out the remainder of the class. So have a solid go at it. See if you can even think of things that might help. I would definitely start by defining the function, and maybe even playing with it on the graphing tool a bit, using a slider to mess with it. It's a totally valid way of doing things. A lot of these higher level questions can be really beneficial to play with on a slider. If a k equals 1, we're going to get that. So if you imagine what changing k would even do, it's attached to the dilation factor and the translation factor. So you can probably imagine it either stretching, it would stretch and shift in a direction. So in this case, it seems to be getting wider and more right every single time. Do we have a k can only be positive, so that's worth considering. K is an element of 0 to infinity, non-inclusive 0. So don't try to test negative numbers, otherwise you'll confuse yourself a bit. But yeah, you can see that as the numbers are increasing, we're shifting right, a bit down as well because we're dilating. Yeah, more or less right and down. Get the feeling if you were to increase it by a lot and then resize the window to obviously now see it. Or at least try to. Yeah, okay. It eventually plateaus onto the x-axis, it would seem. Okay, we've hit time there, so I'll just sort of go through the prescribed answer that I have. So what are some of the things that you could do? Well, turning point of h is always lying on this function. So if turning point is always lying on the function, then what if we just try to find where the turning point of this would be? So you set your derivative equal to 0, and that gives you some values that you could work with. X equals k in this particular circumstance, right? Turning point, derivative being 0. So you know that x equals k for that specific value. So if you then sub that back into your original h of x function to get the corresponding y value, that'll then help you sub in an x and a y to get your n, or at least that's the idea. That's going to give you 1 over k equals k to the power, 2 over k equals 2k to the power of n. Reminder, you just replace this x with a k, and then you've replaced the y with what you got, which is 2 over k. 2 over k equals 2k to the power of n. Simplify, and then, well, just by comparison, you can see that you don't necessarily need to eliminate k. You can just see that this is obviously just the negative index version of itself. N equals -1, which is either a CAS solve or you can just, you can just sort of see that is the case. Cool. All right, that's that one. Tough question. If you're interested, that was a 13% pass rate. This question was, quote, not done well. A common incorrect answer was n equals 1. Damn. Imagine being the person that answered n equals 1, getting all the way there, and then forgetting to put the negative on there. That must suck. Oh well, I guess it's only a mark. Alright, that's about it from me then. I'll leave you guys to it. If you have any questions, feel free to let me know.